Before we start talking about the theorem, this is the only theorem we're doing today. This is our only piece of notes. We're talking about the squeeze theorem. I want to have a quick little discussion about inequalities, just so that like later on this will make sense why I'm saying this. So if I have like 1/3 is less than 2 is less than 4. Do you agree with that?
Yeah.
Okay, so now I want to reciprocate everything. So what will the 1/3 become?
3.
What will the 2 become?
1/2.
What about the 4?
1/4.
So that inequality is not going to hold true. So if you reciprocate everything, what else needs to happen? You also need to change the directions of the sign. Now is this still true?
Yep.
Yes. If you want to... Yeah, Dennis? I'm like nervous about this question. Yeah.
You don't switch the sign if the one is negative and the positive.
Yeah, we're looking at only positives. Yeah. We're not that fancy. So then then you're good with, like, I can then rewrite it back from order least to greatest. Like, this is all fine and dandy. The main thing is, like, if you're going to reciprocate positive things, the signs will also reciprocate or flip. We're okay with that? Okay, so now let's talk about the squeeze theorem. So the squeeze theorem, if you just look at that picture, it kind of just logically makes sense. It says that if you have three functions, so f of x, g of x, and h of x, and it's in the way such that g of x is between f and h, which is what that picture shows, and also what the inequality at the beginning shows, what could happen is if you don't know the limit for g, but you know it's in between those other two functions, if there is an a value containing a except possible at a itself. So it has that value. Now, since we're doing limits, does it actually have to have a value right here, or can there be a hole? There can be a hole. And if the limit of the lower function, so if we know this f, if the limit of f at a equals L, and the limit of h at a also equals L, since g is in between them and both sides of these equal L, what would the limit of g also have to be? L. So all it is it's saying that if you have two functions and you know one is in between them, if both of the sides have the same number to keep the inequality true, the middle part also has to be true. So it's called the squeeze theorem because this function is getting squeezed in between the others as it gets closer and closer to a. It doesn't matter, like obviously it's not going to hold out true to the sides, but if these are close enough together where the above and the below function have the same limit, then the function in between them automatically also has to have the same limit. So it's called the squeeze theorem because you're just squeezing the limits in between them. Okay, we are going to look at the squeeze limit together in kind of a very big picture way. And then when you guys do your homework, you'll be able to see, I don't want to say easier examples, but something where you're like, okay, this makes a little bit more sense. The first problem we are going to solve, and this one you want space, is we're going to evaluate that limit. So the limit of sine of x over x as x approaches 0. This ends up being kind of just a fundamental rule that you will have memorized, and you don't need to show this work all the time. Like, it's just one of those things where you know when you see this, it's always going to have this answer. Can direct substitution work here? No, because what does it yield? 0, 0, indeterminate form, which means, okay, you should probably try something else. Obviously can't be factored. So in order to evaluate this limit, we're going to kind of build a picture. And the best way I can describe this is people who are much smarter than me saw this relationship, worked through it, and they discovered this. So the problem we're solving, that's our solution. We're taking it back up to some really abstract thought, and we're going to get it down to this. But you're going to say, like, why am I starting this way? And the reason I'm going to start this way is because someone smarter than me did it, and they found this rule. So kind of just like believe the process, trust it, whatever it is, but we're going to evaluate this limit, and the squeeze theorem is going to be the thing that helps us. Draw this picture. We are going to start by drawing a quarter unit circle. So quarter unit circle means this guy is just going to go out to 1. And then we're going to take and imagine we have this little triangle right here. And then we also have this big triangle out here. So when we look at this, we're going to say we're in radians. So this angle down here, we're going to call this theta. And now we're going to go through and just kind of notice some relationships. So you notice how we have this little triangle? So we're going to say the little triangle is the littlest thing. And then we have this big triangle. Right? So then we have the big triangle. And then in between those two, why did I start doing that? We have the sector area, which is also created from that triangle. So we have our little triangle here. We have our sector here. And then we have our big triangle out there. So in order, do you agree? It's the little triangle, the sector, and then the big triangle. So we're going to compare those areas because the shapes we know go in that order. Since we're on a unit circle, any point on a unit circle has an ordered pair. Do you guys remember what that ordered pair is? Cosine, sine. So it's cosine theta, sine theta. I'm going to abbreviate just for space. So using geometry, we can actually get a lot of these areas. How do you find the area of a triangle? And then looking at just this little triangle right here, what is its base? What is its height? So here's its base. Is that an x or a y value? X. If we're on a unit circle, what does x stand for? Cosine. So our base is whatever that cosine value is. What would its height be? Sine of theta. The sector, here's where who remembers geometry with radians. How do you find the area of a sector in radians with a central angle? You sure?
Wait, is it the area?
Yeah. There you are. Close. Google it. If you're not sure, Google it.
Theta over 2 pi and then you multiply that area.
We can shortcut that. Google it. I'm serious, you guys. You have fun. Google it. You don't need me to tell you a formula.
Half of r squared
She's
theta.
gonna use it. You tell me.
Yeah.
Yeah.
You guys have more knowledge in your phones than you will ever be able to use. So Dennis says 1/2 r squared theta. So we agree with that. It's 1/2 r squared theta.
And r is
R is your radius, yeah, so that'll end up being 1. And now we have the big triangle. So in the big triangle, again, it's going to be 1/2 base times height. One of those we know for sure because we're on a unit circle. The base. So we for sure know there's a 1 in there. And then it's height. So we are all coming from the same central angle. So from this angle, how would you describe, like, we need that height, that's what we need. We know this base, so what relationship is that? Or think like trig. What's tangent? So tangent theta is opposite over adjacent. So what is our adjacent? What's our opposite? Our height. So what does h stand for? Tangent. So this is the kind of stuff where I say, like, people way smarter than me, they would thought of that. I would never look at that triangle like, yeah, duh, the height's tangent. So that's fine if you don't see that. I don't expect you to see that. I'm just showing you this is the squeeze theorem, the idea of, like, if you know the ends, you can figure out the middle. Can we plug in any numbers here? Like, what's that R? Dennis already said it. 1. We're on a unit circle, so our radius is always 1. And now we kind of just want to start reducing and simplifying away things. First step, what we do? Multiply everything by 2, and that'll make the 1/2 drop out. Now, our end goal is to be able to look at that sine theta over theta, or that sine x over x. So, right now we have a theta. So because we want to be able to relate sine x over x, I'm just going to take all of these and divide them by sine. Which ends up being pretty nice on the left side because we're just left with cosine. We're just dealing with positives. We live in a positive world, Dennis.
Oh, okay. I think it should work because because the squeeze theorem will still work, right? Because
we're gonna assume he's right. Okay. In order to divide tangent over sine, what do we need to know about tangent? Yeah, tangent is really sine over cosine. And when you divide by sine, you're really multiplying by. We'll just do 1 over sine. The reason we would want to write 1 over sine instead of cosecant, well, what are we able to now do? Cancel out the signs. So we know that this inequality is true. And that's all just from looking at that picture on a unit circle of comparing a triangle to a sector to a larger triangle. The thing is, we're trying to get at what is the limit of sine x over x. Right now we have theta over sine theta. So what is the only thing that's making this not correct? Yeah, we need to take the reciprocal of this. Because we're trying to get at what is sine x over x, sine theta over theta, same thing. So we're just going to reciprocate this. It is fancy. We do very few proofs in here. This is one of them. So like, don't expect this on the daily. We're not going to prove everything. Sometimes we just say like, thank you, Isaac Newton. Moving on. When you reciprocate 1 over cosine, what do you get? Cosine. When you reciprocate cosine, 1 over cosine. And since we're reciprocating, what happens to our sines? They flip them. For some reason, that makes me nervous, so I always rewrite it. You don't need to. You do you. So that inequality also holds true. Now, the thing is we're trying to figure out what is the limit as theta approaches 0 of sine theta over theta. That we can't do because it's the indeterminate form. But we now have this relationship that's relating two other functions that are kind of like bouncing it in, squeezing it in. So if we just look at the left side, what is the limit as cosine or as theta approaches 0 of cosine 0? 1. Now we look at the right side. What is the limit of 1 over cosine theta as theta approaches 0? 1. So if we know the left side is approaching a 1 at 0, and the right side is approaching a 1 at 0, since this function is in between them, what is that limit also approaching as it goes to 0? 1. So by the squeeze theorem, we know that the limit of sine theta over theta as it approaches 0 is 1. From here on out, if you see this in your homework, you just write 1 and move on. You don't need to show this. This is just kind of like the squeeze theorem in action. Yes, sir.
So is it the greater than and less than symbols, are those supposed to be greater than or equal to, or how does that?
In this case, again, but we're looking at intervals, so it, like, we don't get too picky about equal and not equal.
Okay.
this gold sheet, there are two limit identities in a way. These ones you should just glue in. These are two that you see them, you just write your answers. So the two limits to remember. You can't do direct substitution, you can't factor, you can't rationalize, you can't algebra your way out of it. These two limits, you just need to have memorized. If you want to be real fancy, you could always do the squeeze theorem for sine x over x, or you could just remember it equals 1. And similarly, we could do the squeeze theorem to show 1 minus cosine x over x equals 0. We're not going to. So these two theorems, you just need to know these limits.